Hi, and welcome to Mr. Queen Science. I am Mr. Queen, of course, and today we're going to be going through some empirical and molecular formula calculations. So I was recently helping some students prepare for the AP chemistry exam, and a couple of them were like, I learned this a bunch of months ago, but as it gets closer to the test, you sometimes forget some of those kind of basic procedural calculations from the beginning of the year. So, based on their suggestion and my own idea as well, I thought it might be helpful to do a few step-by-step guides of different kind of common calculations that we might just not practice very often. So they kind of have slipped by us just as a refresher. So this video is for anyone who might have a little bit of trouble with empirical molecular formulas, whether you are in regular chemistry, AP chemistry, college level chemistry, doesn't really matter, or you just want to learn something new. So let's go ahead and get started. I guess to start off with, we might want to ask ourselves, like, what even is the difference between a molecular formula and an empirical formula? And essentially, they are both representations of the number of atoms or species in a particular molecule. Now, there's got to be some difference, or else we wouldn't think of them differently. So the difference between an empirical formula and a molecular formula is that the empirical formula is what we might say is the most reduced form. I don't mean about no, don't worry about reduction and oxidation. We are not quite there yet. I mean reduced in like how you think of a fraction. So go way back to like third or fourth grade. Who knows what? Probably kindergartners are learning this stuff now. I feel like they're getting smarter all the time. So we take something like 2/4, and you know that you can reduce it to 1/2. So that's what I mean by the most reduced form. Since a formula basically represents the ratio of different numbers of particles in an empirical formula, for example, like we could look at a particle like this, and we might also look at something that is like this. Now, the one on top could be a molecular formula, but it's definitely an empirical formula. It's the lowest, most reduced form of what it could represent. The one below it is what we would call a molecular formula. If you notice, it's the same as the empirical formula, but all of the subscripts have been multiplied by 2, and those represent how many there are of each atom. So why are these both helpful? Well, the empirical formula can be helpful because it gives us helps describe the ratio of elements present in a specific compound. The molecular formula can be more helpful because it actually tells us the actual number of each element in a compound. Okay, so now that we know the difference of what the difference between an empirical and a molecular formula is, let's move on and see how the whole point of this video, which is the step-by-step guide of how to calculate one in a common problem. All right, so here's a little bit more information. We'll probably skip that. To determine the empirical formulas for compounds with the following percent compositions. So I didn't put them all here, but let's just look at one. This compound says it's 15.8% carbon and 84.2% sulfur. When they give us these types of percents in these types of percent compositions, what a percent composition really is a ratio of the mass. Now, when we're finding these formulas, we don't really want to know about mass. We want to know about the proportion of the atoms. And since all atoms have different masses based on their elemental identity, the mass isn't initially that helpful for us. So, how do we begin a problem like this? The first step you want to do is identify the different elements that are going to be in your compound. We have carbon and we have sulfur. So, if you're following along at home or taking notes, now's a good time to start. So I'm going to make room for carbon, and I'm also going to make room for sulfur. And the first thing I'm going to do is take that 15.8%. And this is an assumption I like to make. There's different ways to approach it, but I'm going to pretend that I have a 100-gram sample of this material. Therefore, it becomes very easy for me to say of that 100 grams, 15.8 grams are carbon and 84.2 grams are sulfur. The next step, and this is usually the next step in a lot of things in chemistry, is to convert to moles. The concept of moles allows us to think about the actual number of particles and the proportions of different types of elements in a compound. So, in case you still have a little trouble with these types of unit conversions, what we want to do is find something that has grams in the bottom, so it will cancel out with our other unit, and moles on the top of the fraction. Based on our kind of unit cancellation that you hopefully have been practicing from some of the other videos, we can cancel out the grams and we'll be left with the moles, which is what we want. All right, so how can we relate grams to moles? Now, if you're still having trouble with dimensional analysis, here's a little tip you might have missed out on. Whatever we're multiplying something with by when we're trying to convert it has to equal 1. That's a mathematical kind of identity property. So we can't just multiply it by anything because then it'll become a new number. But if we multiply it by 1, we'll be good. So since we know that there's in 1 mole, there is 12.01 grams of carbon, and that's going to be based on our periodic table. So if you didn't know that yet, although these numbers on the periodic table, oh, I know it's tiny, although they are given in atomic mass units, because of the definition of a mole and how we can use it to essentially convert AMUs to grams, we can just go ahead and assume that these numbers represent grams as well, because they do. So when I checked the periodic table, I saw that carbon has 12.01 grams in 1 mole, and sulfur, so we're going to put our grams on the bottom again and our moles on the top. Sulfur, sulfur, sulfur. Where is sulfur? And sulfur looks like it's 32.06. So let's put that on the top or on the bottom and 1 mole on the top. Okay, so calculation time. All right, so those are the numbers that we have. 1.316 moles for our carbon and 2.63 moles for our sulfur. Now, as you might know, we can't just go ahead and say carbon 1.316 and sulfur 2.63. So what we can do, what our next step is to identify all of our different elements in here. Luckily, this time we only have 2, and we're going to divide both of them by whichever is the smallest amount of moles. So in this case, it's going to be 1.316. And we're going to divide that by 1.316. That's going to give us 1 mole, and that's going to give us approximately 2 moles. All right, and now we have all the information we need to actually write our empirical formula because we know for every 1 mole of carbon, there's 2 moles of sulfur. So that allows us to say that the empirical formula would be CS2. Nice. All right, so let's look at another example. This one's a little bit more complex, and it shows you, again, why empirical formula can sometimes be helpful. So this one says, polymers are large molecules composed of simple units repeated many times. Thus, they often have relatively simple empirical formulas. Calculate the empirical formulas of the following polymers. Again, we're just going to check out one, but there are many more opportunities to practice. And if you still have trouble with this, feel free to comment, send me a message, and I can connect with you and hopefully find a way to really help you understand this at an individual level. All right, so this one is plexiglass. Now, you might say, well, why was it so important? Why does this show why the empirical formula is important? Because in a polymer, you might have thousands or even millions of subunits that are the same, linked over and over and over again. A polymer is like a chain. So we don't want to write something that's like C55,000 and H55,000. That's just like, oh, that's a pain. So the empirical formula, we can just say that it's gives us the information of what the polymer is composed of, and then we can understand that there is a very large amount of subunits here. So let's get started. Enough talk. So just like before, first step is identifying our elements. So we have copper, we have hydrogen, and we have oxygen. Okay. And then we want to, again, assume that this is a 100-gram sample. It's going to make it a lot easier for our calculations. So for carbon, we have 59.9 grams. Whoa, slow down there, boy. Okay, 59.9 grams, 8.06 grams, and 32.0 grams. And as we saw before, our next step is to convert to moles. And as we saw before, again, we want to make sure that our have the same units on the top and the bottom, and our desired unit is at the very end of our series of conversion factors. Now, in this case, there's just one conversion factor. So for carbon, I check my periodic table, it's 12.01 grams per 1 mole. For hydrogen, I like to use this one, 1.01. I know there are different, I know I've seen 1.008, but we're going to just stick to the 2 decimal places for now. And I know for oxygen that it's about 16.0 grams per 1 mole. Okay, so now it's time to do some calculations. All right, so here we go. Looks pretty good. We've got 4.99, 7.99, and we have 2. So typically at this point, if we didn't have whole numbers, we would want to divide all of them by the lowest number of moles that we got, which was 2 moles. All right, and there we have it, our answers. For carbon, we have approximately 4.99 moles. For hydrogen, we have 7.99 moles. And oxygen, we have 2 moles. Now, typically, we would divide all of them by the lowest number of mole that we have, especially if we don't have whole numbers. However, in this case, our numbers are pretty dang close to being whole. So we're going to go ahead and say that we can think this is about 5, about 7, and about 8, and about 2. And let's put that into our formula. So that would be C5H8O2. And if you look up lucite, also known as plexiglass, it's a common polymer, you will see that that is the empirical formula. If we wanted to represent the molecular formula, it would be rather challenging without a molar mass of the object or the material. And even for this one, because it is a polymer, it is just many hundreds, thousands, or millions of repeating units of C5H8O2. So this is where we'll be done for now. All right, before we go too much further, I thought it's important that we might mention what is percent composition, because we've used it in 2 problems, but we haven't actually defined it or even just figured out how we can solve for it. So percent composition, what is it? It's the mass of an element that you're interested in divided by the mass of the entire substance. So, or I guess a better word is the mass of the compound. So when you are asked to find the percent composition of a chemical such as the one indicated here, what we need to do is, first of all, break it down to each of the different elements present. So I see carbon, hydrogen, nitrogen, and oxygen. So just like before, I'm going to kind of space out the different ones. Now I'm going to take the molar mass of the element and the molar mass of the compound, and the total. I guess that's the other thing I want to throw out there. The total and the total. Okay, so by that I mean I'm not just looking for the molar mass of one carbon, I'm looking for the molar mass of the 12 carbon that are present here. So in my calculation, I'm going to have a 12 times the molar mass, which is 12.01, over the mass of the entire compound. So let's calculate that real quick. All right, calculation complete. I got 204.28 as the total molar mass of the compound. That's going to come in handy in the next few questions. All right, before we calculate, let's move on and set all of these up for each element. In the case of hydrogen, we have 16 hydrogen times its molar mass, divided by the total mass of the compound. Then we'll move on to nitrogen, where we have 2 times 14, the molar mass of nitrogen, divided by the entire mass of the compound. And finally, we are going to have just one lonely oxygen divided by the entire mass of the compound. All right, let's do some calculations. Calculation complete. All right, so it looks like for this one, these were the numbers that we yielded. Now you might say those look like pretty small percents, but don't forget they are percents, so we've got to multiply all these by 100. So what's our final percents here? For carbon, it's going to be 70.6% composition of our original compound is carbon. And for hydrogen, we would say it's 7.9% hydrogen. For nitrogen, we would say it's 13.7% nitrogen. And finally, for oxygen, we'd say it's 7.8% oxygen. All right, there we have it. We've calculated the percent composition. Great job. Now there's one last thing we probably want to look at since it was in the title of the video, and that's how to calculate the molecular formula in addition to the empirical formula. So before we jump into the actual calculation, let's figure out how to find that relationship. Now, here's a big clue in the question. If you're looking for molecular formula, they are going to give you the molar mass of the compound. Without the molar mass of the compound, you're not going to be able to discover the molecular formula. You'll only be able to find the empirical formula with the percent composition. In order to find the molecular formula, you need to know information about both the empirical formula and the molar mass. So how do we find the molecular formula from the molar mass? Well, the molar mass of the molecular formula divided by the molar mass of the empirical formula will give us essentially a multiplication factor, a ratio between the two. So that's the number that we're going to look for. That's our unknown. And once we find that scale factor, we can multiply all the coefficients in the empirical formula by this coefficient, and we'll get the molecular formula that we're looking for. Okay, so this is our last chance to practice the empirical formula, so let's get it right. Okay, the dye has a percent composition of 75.95% carbon, 17.72% nitrogen, and 6.33% hydrogen. So our first step is to identify the elements present: carbon, nitrogen, and hydrogen. Our second step is to make the assumption that it is a 100-gram sample. So we can now think of 75.95% as 75.95 grams, 17.72 grams, and 6.33 grams. If you remember, our next step is to convert to moles. We don't want to know how the weights compare to one another. We want to know the proportion of actual atoms in these different compounds. So just as we had done before, we will use the molar mass, which we obtained from the periodic table. Just one of the many helpful things the periodic table can do for you when you're learning about chemistry. Okay, and now let's calculate those moles. So calculating, calculation complete. All right, so here we have it, 6.32 moles, 1.27 moles, and 6.27 moles. Now our next step, since they aren't in whole numbers, would be to divide them all by our smallest amount of moles, which in this case is 1.27. So let's do it. All right, let's do the calculation here. Calculating, calculation complete. All right, so we ended up with 4.98 moles, 1 mole, and 4.93 moles. Now I know it's not quite the whole numbers we were hoping for, but they're pretty dang close. I would usually say if you're within, about 2 to 3%, you're probably good. Probably even a little bit more than that. If you come across numbers like 4.33 or 4.5 or even 4.25, I'd say that's a little too far to round. There'll probably be another step you'll need to use. But for this question, I think it's safe to say that the empirical formula is C5N1, which we don't write, and then H5. Whoops. And just because I've studied enough organic chemistry in my life, I feel kind of uncomfortable if I don't write it out like this. Okay, so that's just an old convention. So C5H5N. And there we have it, folks. That is our empirical formula. We can all go home. Wait, that's not what the question said. So as you prep for the AP test, for the FRQs, or whatever, the multiple choice, whatever it is, please, please, please always double check what the question was asking for. The question actually does not say anything about the empirical formula. The question said the molecular formula. If you walked away right now, that would be the wrong answer. And you know what? If they wanted to be jerks to you on a multiple choice question, they could totally put that as an option. All right, so now we need to determine the molecular formula. So we're going to need to make some space here. And remember, it was C5H5N. Okay, so if you recall, to figure out what the molecular formula is, we need to take the molar mass of the molecular formula divided by the molar mass of the empirical formula. And that will give us a scale factor we can apply to solve for the molecular formula. So our first step will be to find the molar mass of the empirical formula. So let's just kind of do it quick. Carbon's 12, hydrogen's about 1, and nitrogen's about 14. So that should be 74 plus 5. That's about 79 for the empirical formula. And they already told us the actual molecular mass of the compound, which would represent the molecular formula. So we've got 240 over 79. All right, so 240 over 79. Now, it's not quite exact, but it's pretty darn close to 3. So now we have our scale factor between our empirical formula and our molecular formula. So all we have to do is take our empirical formula and multiply all of the coefficients by that. Imagine there's an invisible 1 right here. So that's going to give us C15, H15, and N3. And there we have it, folks. That's how to walk through basic empirical formula, molecular formula, and percent composition questions. There will probably only be 1 or 2 questions like this on the AP exam, but still, it's a pretty basic, pretty procedural calculation to know. And it also helps you understand mole ratios inside of compounds, which can be extended to help you understand stoichiometry as well. So if you found this video helpful, like, subscribe, give me some feedback. Let me know why it didn't help. Let me know why it did. And even more, let me know what types of problems you would like to see in the future. All right. Thanks for tuning in, and we'll see you next time.